Okay, so yeah, I think it's a good place to stop last time. Okay, so because I want to set a new theorem, and then I will just try to improve. Okay. All right. So what is the new theorem? So okay. Okay. So here we have the partial converse. Okay. So yeah. So this is the converse for as a partial converse for the theorem that we just proved last time. Okay. So now let me state. Okay. I think maybe I should just also state the number because yeah, maybe I need to reference it in the future. So yeah. So theorem 7.4.6. Okay. So now that okay, so that x tilde be a simply connected locally simply connected locally compact Hausdorff space. Okay. And okay. So and then that is gamma. Okay. Be a subgroup of the group of the group of self-homomorphisms of this x tilde. Okay. Okay, that x properly discontinuously and freely on x tilde. And freely on x tilde. Okay. Okay, and then that is gamma, big gamma, which is the same thing as gamma of gamma from x tilde to x, which is being defined as gamma take away this x tilde. Yeah, so notice that it's just the x tilde quotient by the region of this gamma. Okay. Yeah, roughly speaking, okay. Be the corresponding quotient space mapping. Okay. Okay, so okay, so we then have the following. Okay. Um, okay, so part A, the quotient space X is connected, locally simply connected, and locally compact Hausdorff. Compact. Hausdorff. And okay, so the gamma from this X to this X is the universal covering space. And then this gamma is equal to the deck transformation group of this gamma. Okay. This gamma is equal to deck. Okay. Okay, so yeah, so actually the yeah, so actually the so there are multiple parts of this theorem. So yeah, I'll just state the first part, okay, and then I'll state the proof of the first part. Yeah, okay. So yeah, so let me go over the content.
Okay, so this X student is a simply Canadian, locally compact host of space, and then let gamma be a subgroup of the group of self-homomorphisms of X student that acts properly discontinuously. Okay, and free on X student, and then let gamma to be gamma of this X student to X, and then which X is given by gamma, like X quotient by it's really X quotient by the relation gamma be the corresponding. Okay, so so this is the setup, and then the quotient space X is connected, locally simply connected. So okay, so this X is like the it's like and then it's connected locally, simply connected and locally compact household. Okay, and then this and then this and then we have that this is the universal coordinate space, and then and then this gamma is exactly the Dexter transformation group. Okay, okay.
Okay, so let's say the proof. Okay. So proof. Okay, so for the proof. Okay, so gamma is okay. So gamma is an open mapping because given that open set W is this X student, so we have that this gamma inverse of this gamma of W is equal to gamma. Sure. This gamma, okay, it's equal to this gamma. So okay, so okay, let's see why this is true. Okay, let's see why it's true. So okay, so let's get back to our get back to the okay, so this gamma is a subgroup of the group of self-homomorphism of the X student, right? And then okay, so now our goal is to show that okay, so gamma inverse of gamma of W open set. Okay, so basically okay, so what is gamma? Oh, wait.
think here it should be gamma acting on this W. Okay.
It's the union of open. Okay.
Yeah. So it's the union of. Okay. It's the
Union of the open set. Yeah.
open set is small gamma of W, where this small gamma is in this gamma. Okay.
Okay, so let's see why this is true. Okay, so
Okay, so I want to show that this is okay. So basically, what I do is that okay. 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 So if I take any okay, so if you take any, so that what is the element? Okay, so let this x tilde to be in this set. Okay. So this implies that gamma of this x tilde is equal to, sorry, it belongs to gamma of this W. Okay. And then okay, so this implies that this gamma of this x tilde is equal to gamma of, let's say, small w tilde. Okay. So okay. Okay. So why is it true? Okay, because yeah. So because yeah. So remember that we have the yeah. So remember we have the
we have the theorem saying that if you fix a point upstairs, right?
So then the mapping from the deck transformation group to this fiber. So if you specify a center is W, is a bijection, right? And then yeah, so this map is given by, I think it's phi mapped to I forgot. Let me see. Yeah, so phi goes to yeah, so phi goes to phi of this base one. Okay. Okay, so now yeah, so since here we know that these are all in the fibers, right? So now what we have is that Oh yeah. Because this is a fiber. This is in the fiber. This actually is also in the fiber, right? So therefore, okay. So now since maybe I change to gamma. Okay, maybe I change this to this small r. Okay, small r. Sorry, small r. Okay. So then, okay. So maybe since this is a bijection, yeah. So okay, and we know that this x tilde is also in this fiber, right? And then so yeah, so we have that. So there exists a gamma in this Deck transformation group. Okay, so let's say Deck of gamma such that this small r, this small r in this Deck transformation group of gamma such that this r of omega tilde, right, is equal to x tilde. Okay, and then yeah, because of the break, yeah. Okay, so then okay, so then what do you want me to show? Hold on 1 second. What do you want me to show? Oh, yeah. So since this W is in W, right? This W tutor is in W. So therefore, yeah. So then we have the result, right? Because this W tutor is in this W, and then yeah. So that this implies that, okay. So this implies that this x tilde is which is equal to this, right? And then okay. All right. So now let's see. Take the other inverse direction. So that so maybe I use this letter so that maybe I let this one to be equal to this one. Maybe I use this one. Okay, I use yeah. So then so by definition, x is equal to some small r of w tilde. Yeah, where this w tilde is in this w, and then okay, so then you have that. So this implies that. So because this gamma is a so this implies that this gamma of this x tilde is equal to gamma of I want to say of this w tilde. This implies what? Uh, let me think. So let me check. Oh yeah. Okay. Yeah. So so then okay. So what do you want to show? So I want to show that. Okay. So I want to show that these. Okay. Okay. I want to show that this x tilde is in this space, right? So namely, oh. Oh, okay. I think it's done, right? Because this gamma is a yeah, this gamma is a covering is a yeah, this is done. Okay. Yeah. Okay. All right. So all right. So let me think. Yeah. Okay. Okay, so let's see why this is a union of open set. So why is the union of the open set? 很难。Oh, okay. Okay, I think so why is union of open set? Okay. Okay, I'll leave it to you to verify that it's union of open set. Okay. So then, okay, so this is true. Okay. So and then this is open mapping because wait. Oh, okay. Wait. Open mapping. So why this is open? Gamma inverse of this set is open. Okay. I think this is open. I think this is open because if you take the inverse of open set, because this gamma is a wait. This gamma inverse is a continuous mapping, right? It's a continuous map, so why is it open? Okay, I want to show that this is open. Okay, so it's a union of inverse of this set is open. It's open. The inverse of the set is open. Yeah, I'm not. Okay. Yeah, I'm not so sure. Okay, so I'll leave it as an exercise. So I know that. Okay, it's definitely true that this gamma inverse of this set is open. Okay. And then why this implies that this set is open. Um, Sorry, I can't put on my mind. Okay. Anyway, so yeah, let's continue. Okay. Wait. No. Given an open set, I want to show. Wait. I know that this gamma is continuous, right? So the inverse image of one set must be open. But we can, yeah, but and this W is open, right? If you take gamma inverse of W, but it doesn't help, right? Given an open set W in its X tilde, gamma inverse of gamma W is equal to gamma acting on is open. Okay. But why? But why this implies that this gamma is continuous map? Yes. Inverse continuous map means okay. Okay, so I know that this gamma inverse is continuous, right? So what happens if you have a continuous image of a? So is it true that if you take the continuous the inverse image of a, can you have a continuous function that if you have the, yeah, if you have the inverse image of a non-open set under a continuous function and the image is still open, can you have this property? So if you have a continuous function and then the set is not open, then then the image is open. Can it? Okay. I don't know. Sorry. Okay. So inverse image of an open set of a non-open. can you have the inverse image of a non-open set? Yeah, we don't know anything about the non-open set, right? Just a non-open set. But we know that the inverse image is open, right? So, yeah. But this gamma is a wait. This gamma is it a complete map or something? Oh, okay. Maybe there's yeah, I'm trying to say that maybe there's something special of this gamma, right? This gamma is like yeah, this gamma. Wait. Yeah. Yeah, this gamma is like it's being defined as yeah, this gamma is being defined as if you take any point, you map it to equals class, right? That gives you something. So okay. So if you take yeah, so you take if you take equivalence class downstairs and then you map it up, right? And then wait. I think like that gives you what? That gives you the fibers, right? That gives you the fibers. And then together, yeah. Why does that given an open set W it is x tilde gamma of W. I know that this gamma of W is I want to show that it's open, right? And then and we know that the gamma inverse of this set is union of union of open set. We know that the gamma inverse of okay. What is the gamma inverse? So the gamma inverse of this set. So basically, okay. So basically, if you take the gamma inverse of the wait. Gamma inverse is like the fibers here, right? What? Okay. Yeah, it should be that. Okay. And then this gamma of W is in this X. Where is X? Yeah. So this is the quotient topology. Then take the okay.
Okay, I think that maybe it has something to do with the quotient topology. Let me see. Okay. Let me think. Okay, so the quotient topology is the topology. Okay, so okay, so the topology on this wait. Yeah, so the topology on X. Yeah, so the topology on X is being defined to be the set of all oh, okay. It's a set of all U in this X such that gamma inverse of this U is open in this. Okay. In this yeah, in this X tutor, right? Okay. Okay, so this is the definition of a quotient topology in this X. Okay, so now, by the definition of quotient topology, this set open, right? Okay. Okay, good. Okay, good. All right. Yeah. Okay. Okay. I think this shows the result. Okay, so it shows the result. All right. Okay, so now let's see what happened. Okay, so this is the exercise. Okay, so